Good afternoon, I am Mr. Ish. Thank you for joining me for this video. I had an email inquiry from one of the viewers having an issue with volume determinations, and therefore I'm presenting something with regards to what that email had requested me to do. So you're having a specific function, but you're looking here with improper integrals involving some sort of an infinite limit, and how could one, if it was even possible to do a volume determination? Well, it would basically depend on the function, and it would depend on the integrand and the circumstances of that integral. If you're looking here at y equals 1 over x from 1 up to infinity, you know y equals 1 over x is a hyperbolic function curve, but if you were to limit it from 1, you would have a curve which would look something like that. Then you're looking at it all the way up to infinity, from 1 to infinity, and you're looking at all of this right here, and then you're rotating it around the x-axis as I have. You can easily generate what could be a good volume over here, and it would probably result in an acceptable volume determination, because eventually everything here would zero out, especially when you bring in the radius determination. See, you have a 1 over x, a variable here with the order exponent or degree of 1, but when you do the radius determination from your x-axis, you're looking up at your curve, you have a radius here of 1 over x, but when you convert the radius into an area, you have a pi over x square. The fact that you generated here is square, it makes it very possible now that you may not have divergence come into play. So the volume determination is this. You're looking at something like this. With a pi sitting outside, you have a dx over x square, and then you have from here 1 up to infinity. And think about it, if you were looking at this function 1 over x and you do limit as x approaches infinity, 1 over x, you know it very well equals 0. The limit is indeed possible here at infinity. However, if supposedly you're doing limit for the same type of function as x approaches 0 from the right, 1 over x, now you know you're going to increase towards positive infinity, because as you're coming close to your vertical asymptote, your function is exceeding out of bounds. But here you're approaching a horizontal asymptote, so the limit over here at infinity does exist. Therefore, prudently and logically, the volume should exist as well. And you have everything set up over here. When you do if you want, you have an improper integral type 1, you could even have brought in a limit as t approaches infinity. You're looking here from pi 1 up to t. You can do that if you want, and dx over x squared, but you don't have to. The antiderivative here is x to the minus 2 plus 1 over minus 2 plus 1, because I'm bringing it up. And then you're looking here everything with regards to the limit as t approaches infinity. We have t and a 1. What does this bring? You have here a minus 1 over x. How do I have that? Because I'm developing a minus 1 exponent here and a minus 1 here in the denominator. The minus 1 I've pushed out right over here. I pushed this minus 1 right here and I attached it to pi. Now what I'm really doing, I have a limit here, t approaches infinity. I have a minus pi, but then I have a 1 over t and minus 1 over 1. This 1 over t zeroes out because 1 over infinity is a 0. You have a minus 1 times a minus pi, and you end up having a volume here of a pi. So indeed, type 1 improper integral, for this specific function here, rotated on the x-axis, a volume does exist. The volume happens to be pi. The volume of this entire solid, which looks like a large horn, a very long horn, the volume of this entire solid here is going to be a pi, an interesting outcome. Let's look at one more. We can make it slightly different. We have y equals e to the x. We can look at it from minus infinity up to 1 and including 1. So let's demonstrate that indeed here we will have a volume determined. Imagine you're out here at minus infinity and you're here at 1, e to the x right here. That's what we're looking at in terms of our curve and our limit. If you were to bring it out here, you got your solid. It'll be a through and through rotational solid, all of that. This limit as x approaches minus infinity, e to the x, it does have a very viable answer, because what you're doing is e to the minus infinity, which is 1 over e to the infinity, which here is 0. Limit as x approaches minus infinity for e to the x, you have a good answer, 0. Therefore, by all manner of respect, you should ideally have a good outcome here. It's a type 1 improper integral. You know from your x-axis looking up towards the curve, you have a radius here which is e to the x. The area here must be pi r square, which would be pi e to the 2x. That right there is your area, your cross-sectional slice of this circular slice which will integrate from one interval limit to the other. Everything here is, as in the previous example, was circular cross sections with the radius, areas, everything. Volume over here with respect to x, you have a pi sitting outside. You can do here limit if you want, limit as t approaches minus infinity, because the limit does exist. I've shown it to you right here. You're looking here from t up to 1. You have this right here, your area x. Remember, with volume you're doing an integration of your area over your lower and upper limit from one to the other. You have e to the 2x dx. That's your integrand over here. So let's bring this into perspective. Limit as t approaches minus infinity. You don't even have to do this if you don't want to. You can. You have a pi sitting outside. What's the antiderivative of this? It's not hard. It's e to the 2x over 2 from 1 to t. Lower limit, upper limit. Remember, for these exponential functions, their antiderivatives, when you're doing them, is e to the ax over a. That's what it is, and that's exactly what I have. The a over here happened to be a 2, so it came down as a denominator. We have here limit as t approaches minus infinity. We're looking here at a pi over 2. The 2 has been pushed outside. You have e to the 2x from 1 up to t. Now let's integrate it. We have a pi over 2. We're looking here at e square minus e to the minus infinity. Because 2 times minus infinity is minus infinity, it's kind of irrelevant to even bring in all of these, because you know e to the minus infinity is going to zero out. You're looking at 1 over e to the infinity, which is 0. You can zero all of this out. In the end, your volume here, we can write this out here, volume is going to be pi e square over 2. You can get a numerical output here with regards to your calculator. You don't need to, but this right here is your volume and it should be good. This rotational solid coming here from minus infinity and ending here at 1 indeed has a very viable and acceptable volume, and it's right there, pi e square over 2, because your limit existed over here. It was a type 1 improper integral and everything worked out. There's complete convergence here with regards to your integrand and your interval, and it's done. So keep in mind, it depends basically on what your interval is. It depends also on what will be your integrand. It also depends on the fact right here if your limit will indeed exist. And that's about all I want to present to you in this video. Thank you for watching. Have a nice day.